So chemistry, you say? So it was important in rocket fuel, making sure that they had the right rocket fuel, so that would provide the appropriate thrust so that you could escape Earth's gravity. And in the development of safe and effective spacesuits, so that you could go in the rocket and also walk around on the moon. And finally, air handling, because you had to take all your air with you when you went into the vacuum of space. So that was a big issue as well. So these are the three areas that we're going to focus on. Just, you know, a little smattering of things, because there was so much involved in this mission. So fly me to the moon. So Saturn V was the rocket that they used to loft the space, I'm losing my words, to loft the astronauts, there we go, into space. And so the Saturn V rocket was used for Apollo missions and for Skylab. And we can see that it was a pretty traditional rocket design. And so it was used from 1967 to 1973, and it was used to move astronauts and materials into the Earth's orbit and to do moon missions. It used liquid kerosene, liquid hydrogen, and liquid oxygen. And it had a lift capability of 130 metric tons, and it had a thrust of 7.5 million pounds. Now compare that to the Space Shuttle, which was used from 1981 to 2011. And the idea there was that you're going to have a recyclable space shuttle that could land like a plane. And so you can see the design is very different for the Space Shuttle. Now you have external fuel tanks, and you have the Space Shuttle riding on top. And that was used to achieve Earth orbit and go to the International Space Station. And so that used solid fuel, liquid hydrogen, and liquid oxygen. So it needed less space because the fuel was solid. And it had lift capacity of 24 metric tons because it didn't have to loft as much into space. And so, but it had to have equivalent initial thrust to escape Earth's gravity. So it had 7.8 million pounds of initial thrust. We can see that the plans for the Orion Space Launch System is sort of a hybrid of the two. You're going to have your fuel canisters arrayed on the sides, and also main fuel in the center, but you're also going to have more of this rocket shape in the center, and the Orion space capsule itself is reminiscent of the Apollo space capsules. So what is the propellant that's going to get you out of Earth's gravity? So I focused on SC1, the stage 1. So if you look at SC1, you are going to see that there are two main tanks on there, the two main tanks. So you're going to have oops, let's go back. There we go. You're going to have your kerosene fuel here, and you're going to have your liquid oxygen here. So kerosene fuel is below, liquid oxygen is above. And you've got 203,400 gallons of kerosene fuel. I mean, it's just a crazy large amount, equivalent to 770,000 liters. And then equally, you've got 318,000 gallons, or 1.2 million liters of liquid oxygen. That's just, I mean, just astronomical amounts compared to our everyday lives. So let's look at the kerosene. Why do you have that much kerosene fuel? So you want to have accelerated combustion of kerosene with oxygen so that you create a tremendous amount of thrust in a tiny amount of time so you can escape Earth's gravity. So when we look at kerosene's chemical composition, it is a hydrocarbon, so it's made of carbons and hydrogens. It's about 70% branch, straight chain, and cycloalkanes, and about 25% alkyl benzenes, and about 5% olefins. And it's a heavier fraction compared to gasoline. Gasoline is a lighter fraction. Its flash point is 37 to 65 degrees Fahrenheit, degrees Celsius, which is 100 to 150 degrees Fahrenheit. And that is the point at which the vapor portion of your liquid fuel will spontaneously ignite in air. Conversely, its ignition temperature is actually higher. So if you're going to ignite the liquid, you have to be at 220 degrees Celsius, which is 428 degrees Fahrenheit. So that's a problem. Your vapor will spontaneously ignite at a temperature lower than the ignition temperature for the liquid. And so that is a problem in handling. You have to make sure that you don't have a lot of vapor around, because it'll go up in flames before you want the system to go. Now the freezing point is minus 40 degrees Celsius, which happens to be at the point where Fahrenheit and Celsius scales cross over, so it's numerically the same value in Fahrenheit, or 233 Kelvin. And that's going to be important because of the liquid oxygen. So the liquid oxygen is a liquid between 54 Kelvin and 90 Kelvin, which is minus 219 to minus 183 degrees Celsius, or comparably minus 362 to minus 297 degrees Fahrenheit. So that means that your freezing point of your kerosene is far above the liquid point of your, or liquid range of your liquid oxygen. So that means the liquid oxygen can never meet the kerosene, because then it will freeze the kerosene will plug up, and you'll no longer have flow of your fuel to your engines. And so that was a serious concern, because they needed liquid oxygen. We'll see why in a moment. So they need a whole lot of oxygen in a small space, relatively speaking. And so that meant that they had to have effective cryogens to hold the liquid oxygen there, but they also had to separate it from the kerosene, and they had to be thermally separated so you didn't freeze the kerosene and stop the flow of fuel to the engine. So there's our gallons of kerosene fuel. Okay, so how much heat energy are you getting out of that? So we assume an average composition for kerosene. So we're going to assume C13H28, that's sort of between 10 to 16 carbons and 22 to 36 hydrogens. And so if we do the balancing of our chemistry, we find that for every kerosene, average kerosene molecule, you're going to need 21 oxygen molecules. So there's a 21 to 1 ratio there for complete combustion to carbon dioxide and water. And so we can look up what the enthalpy of reaction of kerosene is. It's been well studied. And so depending on its exact composition, it'll have a range of 43.1 to 46.2 megajoules per kilogram of heat energy that is given off. That's why it has a negative sign. And so if you consider that you've got 770,000 liters of kerosene, knowing its density, which is known, you can figure out how much it weighs. And once you know how much it weighs, then you can calculate its heat output. And its heat output is 27,500,000 megajoules. So that's a lot of heat output. Now, obviously, you want to turn most of that into thrust. But if you think about it as just heat output, that's enough to boil 32.5 swimming pools of water. So that's just a tremendous amount of energy that you're giving off. And so, yes, it mostly goes into thrust. With the gas expansion, it's going to push the rocket up. So that's what we're looking for. Now, if you are going to have that much kerosene combust, and each molecule of kerosene is going to need 21 molecules of oxygen, you're going to need a whole lot of oxygen. So let's go look at that calculation. So we focus on the oxygen needs now. And we see that if we have 770,000 liters of kerosene, that's going to require 3,300 kilomoles of oxygen. So that is 3,300 times 1,000 times 6.02 times 10 to the 23rd. So that is just an amazing amount of oxygen, just crazy amount. And so that is equal to, if average air is 20% oxygen and its density, you need 8 million cubic meters of air. So there's no way you can have enough oxygen from the air to combust that kerosene in a concentrated space in a short amount of time. It's just not going to happen. And since it's not going to happen without extra oxygen, you have to provide that extra oxygen. And so the most efficient way to provide it is to condense it into the smallest space, and so that means making it liquid oxygen. So if we look at how many gallons or liters, 1.2 million liters of oxygen that you have in the liquid oxygen tank, is that enough? So yes, it definitely is. And that's because liquid oxygen is also used for the thrusters in space combined with liquid hydrogen. So they needed liquid oxygen not only for the SC1 stage, they needed it later on as well. So this is plenty. So they had to develop efficient cryogenics to be able to handle that liquid oxygen. So it's like making a really, really good thermos. And so they had to make a really fantastic thermos to hold the oxygen at the very cold temperatures. So now Saturn versus the space shuttle again. Let's look at something else. So we can look at the Saturn. It had all of its components in that rocket shape, and so that meant it had to be tall, and it had to be subsequently heavier. When you move those fuel containers outside, you can make something that is more compact, and you don't limit the space that you can have on your eventual space component. So the space shuttle actually had more space in it. So now that we've talked about rocket fuel, we can talk about the spacesuit now, because the spacesuit has some really cool components in it. It's harnessing chemistry to create great technology, is the way I think I view it. So, you know, there's also the art and the craft of putting things together in addition to the chemistry of the components. So we can see in a spacesuit, you've got a lot of different parts here. And so I have a little black and white diagram from the NASA history website on the Apollo 11 mission. And you'll see all of these different components as line drawings. And so you've got your hat, you have your urine collection assembly, you have your fecal containment, you have your liquid cooling garment, you have your outer garment, you have your gloves, your boots, your helmet. This was for biometric tracking to see how their heart rate was doing and pulse and so on. So if we look at it, here's the grand scheme of it. So if you start on the left, you've got the fecal containment system, which is a diaper, because you're stuck in your spacesuit. And you have your helmet, you have your communication system, you have your visor for being out on the moon. You have your air handling, so your gas handling system, which we'll talk about in a bit. You saw the gloves and the boots. Urine collection transfer assembly, again, because you have to pee in your suit and you don't want to literally pee in your suit. You have the biomedical belt where they took a lot of biomedical readings to see how the astronauts are doing, and then you had the liquid cooling garment. So we're going to focus on the pressure garment assembly, and then we're going to go talk about the liquid cooling garment, and then finally we're going to talk about the air handling. So this is what we're going to focus on first. So what do you need in a spacesuit? You're going to be out in the vacuum of space. It needs to be impermeable because you don't want to lose yourself out into the vacuum of space. You don't want to lose your air out in the vacuum of space. And you don't want to be impacted by micrometeoroids, because micrometeoroids would slice through your spacesuit if it was permeable. You want it to be pressurized because you have to carry your air with you. Vacuum of space is not good for breathing. You want to have good gas exchange because we inhale in oxygen, we exhale out carbon dioxide, and we want to keep that balance such that we're doing that. We don't want carbon dioxide to build up. We need to have good thermal control because it's going to be impermeable. It's also going to keep heat in and cold out. We need humidity control because it's a closed system, and as we breathe out, we are constantly breathing out some humidity, some water vapor, and you want to make sure that water vapor doesn't condense on your helmet and make it impossible for you to see. You want to be mobile because you're going to want to walk around or drive around in your lunar module across the moon's surface, or what current astronauts have been doing, taking spacewalks on the International Space Station and on, losing my words. Kepler is replacing the one I'm thinking about, Hubble, the Hubble Space Telescope. And so for all of those, the best materials are going to be plastics. And we're going to be looking at a lot of composite materials made of different plastics and also other components. So really, plastics are the secret to making a successful spacesuit. So this is a low resolution picture that I got from the NASA history webpage about the Apollo 11 mission. So as I talk about these different components, I'm going to be overlaying the words in a dialog box that has it more clearly presented. So there are many, many layers to a spacesuit. It's definitely the ultimate in compositing and in making different components. So The first one we're going to look at is a liquid cooling and ventilation garment right here. So that's the one against your skin. So it's made of nylon trico. It's going to have a liner, and so that's going to be the outer layer, and that's made of nylon and spandex. Spandex, so it has stretchiness. The next one is going to be the pressure garment bladder. So that's going to maintain the size of your spacesuit. We're going to talk about why that's important. You have the restraint. Again, that's something so that it maintains the shape even in the vacuum of space. And then you have 3 layers that are meant to keep you from freezing or boiling. Because remember, you have no atmosphere between you and the Earth and the sun's rays. So if you're directly in the sun's rays, you're going to feel the heat very quickly. If you're out of it in shadow, you're going to get cold very quickly. So you want to moderate and make sure that you don't have that thermal loss or thermal gain. So you have 3 layers for that. The first one is a thermal micrometeoroid garment liner made of neoprene on ripstop nylon, nice strong. Then you're going to have the thermal micrometeoroid garment liner, which is multi-layer aluminized mylar. So that's a composite material that's pretty interesting. And finally, you have the garment cover on the outside, which again is going to protect you. And it's also going to have some fire protection in there. We're going to talk about that as well. So you have all these different layers put together. And also you're going to have some kind of structural framework as well that's going to be built into the suit. And then you also have to have your ports, and you have to have your helmet lock and all those other parts built into it as well. So if we look at it, the first one is going to be nylon. So we have nylon is used throughout the spacesuit in different layers. So nylon is a polyamide. And so it's going to be composed of a diacid. So you can see the diacid has the oxygens, those are the red ones, and everything else is going to be carbons with hydrogens on it. And that is combined with a diamine to make a diamide. And so the nitrogens are the blue atoms there. And again, you have carbons and hydrogens in between. And so these all string together to make long, long, long fibers. And so nylon is long and strong. Next one is going to be Dacron. So Dacron is important plastic that was in this. And so this polymer is actually a polyester. So it's polyethylene terephthalate. And so you can see you got this nice benzene ring here. And then it's an ester because it's got these oxygens in the structure. And so again, you're going to have all these parts that are going to string together, making nice long Dacron fibers that then you can weave. The rubbery components, those are going to be neoprene. And so those are going to be artificial rubbers. And so those aren't fibers, they're more like an amorphous semi-solid that you think that has flexibility. Spandex is actually a woven stretchy fiber. And that's because of how it's put together. So it has components that are wrinkled when it's at rest and then can be stretched out when you need something to stretch. And the last one's going to be Mylar. So Mylar is super cool because that is a composite. So now we have an idea of some of the chemical components. Now let's go look at Mylar. So Mylar was used as a thermal shield and as a thermal blanket. So the picture from the thermal blanket is the one that has the most interesting details on it. So it's going to be the same kind of construction that is in the Mylar that is in the spacesuit as well. So what you see is that it's many, many, many teeny tiny layers that are going to be alternating. So they're going to be Mylar, which is a composite Dacron, which is not pulled out into fibers. It's actually laid down as a sheet. And so you're going to lay down a really, really thin sheet of Mylar, and then you're going to deposit on a really thin layer of aluminum metal, and then you're going to put on another thin sheet of Mylar, another layer of aluminum, and so on and so forth, and so on and so forth. And so you get this amazing multi-layer cake with alternating layers. And you want the aluminum in there because the aluminum is a really good thermal barrier. And so, and also when it goes down, it's going to adhere very well. And as long as it's made well, you're not going to have pores as well. So when the aluminum lays down, as long as it's a micro layer, not a nano layer, you're going to make sure that you get something that does not have pores. And so the Mylar, you're going to put that down carefully so it doesn't have pores either. So the whole thing is going to be impermeable and also be a thermal shield. And so if you look at this, you have 15 layers of alternating aluminized film, and that is 1/2 of a millimeter. And then you've got 10 more layers that are 0.15 millimeters. And then you have an outer layer that is thicker that is going to help hold it together. So you have an outer layer on both of them. So it's got some thick icing on the bottom, thick icing on the top. And then you have cake and jelly and cake and jelly and cake and jelly and cake and jelly. And so that is how Mylar is put together. So when you look at a helium Mylar balloon that you buy for a party, you should, be sort of amazed at it. Even though we think it's just everyday stuff, it's amazing the technology that went into creating these, what we think of as fun party balloons. So now you have all this thermal barrier that you've built into your spacesuit, and we are warm-blooded creatures. That means we are always putting out heat energy. If we are always putting out heat energy and we hold it in close to ourselves, it's like being wrapped up into a really efficient blanket and overheating. And you'll end up dying of heat stroke if you don't have some way of controlling your temperature within the spacesuit. So what they have for that is they have a liquid cooling garment. So again, this is a composite product, and it's got different plastics that are used in it. So you have on the bottom, you've got a lightweight nylon. Here, I can do an annotation. So on the bottom, you've got your lightweight nylon. To carry the water through, you're going to have your Tygon tubing. So there's your Tygon tubing right here. I can color this in. There's your Tygon tubing. And then your stretchy holding layer is going to be your spandex layer, and that is on the other side. So that will make that blue. So there's your spandex layer. And you can see the spandex is an open, flexible weave. And so that's what gives you the nice flexibility for movement in it. And so you can see in the liquid cooling garment here, as it's demonstrated on this model, we can see that the liquid cooling garment also has the in and out ports available. So that you can hook it into a liquid source, a water source that you're going to cool, so that that can go through and keep you from overheating in your spacesuit. Let me clear my drawings. All right. And now we're going to go on to our next one. Okay, so I talked about before that you need to have pressure containment. And the problem is that when you go into the vacuum of space, so you're stepping out from the atmosphere that you've held in your spaceship, and you're going out into the vacuum of space. What happens is that all the pressure that you have inside that you like to live in, we like to live in the atmosphere pressure of the Earth. Then what happens is that that pressure inside the spacesuit is going to push out because the vacuum is not providing any pushing back. And so what happens is that your spacesuit, if not given some kind of rigid exoskeleton, is going to blow up. And it could actually pop if your materials are not strong enough to contain that pressure. And so it also reduces mobility. If you look at the end of the astronaut's dilemma, when the spacesuit is fully inflated in this cartoon example, it's sort of like Maggie Simpson in her snowsuit. She looked like a starfish and she could barely move. That's because she was so packed in there with so much other stuff around her. It was sort of like pressurizing her into place. So you don't want that. So you want some kind of rigid structure that is going to help hold your spacesuit in shape so it doesn't overinflate in the vacuum of space. And so I like to use this lovely article to sort of, focus on that. And so Neil Armstrong's spacesuit was made by a bra manufacturer. And actually the seamstresses at the International Latex Corporation in Dover, Delaware were extremely skilled. So they had experience with stretchy fabrics and layering. And they were also really good at precise hand stitching. The stitching errors in a spacesuit had to be less than 1/32 of an inch because the astronauts' lives depended on it. So the outer layer, which I said had to have some fire protection, that was actually Teflon coated glass microfibers. And they can, we know that glass microfibers are really good insulators, and that's the insulation that many people have in their homes. And it withstands up to 1,000 degrees Fahrenheit or 540 degrees Celsius temperature. And they needed the fire protection because the Saturn V rocket was, it was potentially very dangerous. It had, you had all those gallons, just thousands of gallons of kerosene, and then all the thousands, 1.2 million liters of oxygen, so thousands of gallons of liquid oxygen. And that was just a combustion nightmare. And they did have fires in many of the Saturn V rocket attempts and earlier Apollo mission attempts. And so fire was an ever-present danger for these astronauts. And so for that reason, they built in fire protection into the spacesuit so that the astronauts would not burn to death if there was a fire on the launch pad. And finally, we're talking about the astronaut's dilemma, and here it comes in. So the seamstresses had to stitch in the steel aircraft cables to provide an exoskeleton to hold that spacesuit in shape over the body. And so it had built-in hinges and other mechanisms so that you could move somewhat normally in the spacesuit. And so that way it maintains its shape under pressure when you went out into the vacuum of space. But Neil Armstrong had a wonderful quote. He said, "Its true beauty, however, was that it worked." And that's the thing, anytime these astronauts, these pioneering astronauts went into space, they were taking their lives into their hands. They thought that they had, about a 5 to 10% chance of coming back alive if they were lucky. So this was an amazing effort for them. And they really depended on all these people to come together to create a system that made it work for them. So now we go to the portable life support system. So remember, you got to carry your air with you, and you have to also carry a means to get rid of your exhalations, your carbon dioxide. So let's look at that, the portable life support system. So breathe in, oxygen, breathe out, carbon dioxide. So we got to deal with both of those. So in this backpack, you're going to have a whole system that is going to work together to make sure that you can breathe. You're going to have oxygen tanks that are external to the backpack. You're going to have disposable carbon dioxide absorber, which I have highlighted in the blue circle. So there it is. And it's lithium hydroxide and charcoal canister, and it can be exchanged out. So you had the oxygen tanks on the outside, so you could always put in new oxygen tanks or refill your oxygen tanks. And then you also had these canisters that absorb carbon dioxide that were disposable. You could take the used one out and put in a fresh one. And so why have lithium hydroxide? Because it gives you a nice clean chemical reaction. So your lithium hydroxide is a solid. It's going to soak up the carbon dioxide that is being pushed through the canister, the porous canister. You can see how the canister has a whole lot of little holes in it. And the carbon dioxide is going to react with the lithium hydroxide to make lithium carbonate and water. And so the lithium carbonate will sequester the carbon dioxide in a solid, and therefore you aren't going to be rebreathing your carbon dioxide again, which you don't want to do. So you have a solid absorbent, a solid carbonate product, and plus if you use one of the lightest metals on the periodic table, that's why we use lithium in computer and phone batteries now, because it is the lightest metal on the periodic table. Then you are minimizing the weight that you have to put into this backpack, and that was really important. So you also had to have a carbon dioxide sensor. So this was a little bit more of chemistry melded with technology. And so it was like chemical and mechanical engineering and a little bit electrical engineering all working together. So you could tell when your canister was getting spent so that you didn't start breathing in your carbon dioxide and pass out. And the other thing was we said that there's charcoal in the canister, and that was just a deodorizer to make sure you weren't, breathing stinky stuff, especially if you're sweating when you're working. So we've gone through this overview, this fantastic overview of some little parts of the hidden chemistry of the Apollo 11 or the Apollo missions, but I was focusing on the Apollo 11 one particularly. And I really focused on these because these got translated into practical applications in our everyday lives. Now you see cryogenics. What do I need cryogenics for? I mean, I can buy a thermos at Target or Walmart. What's the big deal? When you think about magnetic resonance imaging machines, their magnets have to be cooled to liquid helium temperatures. And so the cryogenics technology to develop a really efficient thermoses, and really large ones too, to contain the liquid oxygen and liquid hydrogen. Liquid hydrogen and liquid helium have similar liquid ranges, enabled the development of really good thermoses, essentially, cryogenics technology to enable MRI machines to be envisioned and then put into practice. The emergency thermal blanket, that's Mylar, and then we talked about the balloons before, the helium balloons. Those helium balloons that are made with Mylar lose their helium very, very slowly because they're only going to lose it through the seams. It's never going to lose it through the Mylar. The Mylar is impermeable. And so with the idea that Mylar also is a really good thermal barrier, it won't let heat out or heat in. It just won't let heat across its blanket, its existence. So that has gone into making very lightweight emergency thermal blankets, and you find those all over, and they're often, given out at, disaster sites to keep people from freezing, if that's one of the issues. Also, when we talked about that beta cloth on the outside, that combined with Mylar has resulted in superior fire-resistant protective clothing for firemen. And so we have an example of a fire suit worn in the upper right-hand corner, and you can see that it has that reflective look, and that's due to the incorporation of the Mylar, but it also is going to have that beta cloth technology in it with the embedded glass fibers in a plastic matrix. And so that enables firemen to stay safer. And finally, when we think about air handling as well is another place where this technology has been really important, and that's going to be in scuba rebreathers. So the idea of having a carbon dioxide absorber and a carbon dioxide sensor, that has led to a development of the modern scuba rebreather, which uses slightly different chemistry in it, but it's going to be the same idea, and you need that carbon dioxide sensor again. So scuba rebreathers really are the generational outflow or evolutionary outflow of the development of air handling for astronauts in the Apollo missions. And that's everything I have. These are my references. Thank goodness for NASA. They have a public website that has a lot of their stuff archived and made it very interesting for me in my exploration as a curious chemist. So now I can take your questions. Remember, questions in the chat feature will be answered. My goodness. I know some of my students are watching, so you guys, I'm putting you on the spot. You got to ask questions. Skylar, do you have a question? Oh, okay. Do you know what was used to cool the water used for the liquid cooling suit? For example, in a computer system, a fan is used to cool a reservoir of water. I think it probably was a fan. I'm assuming it was a fan that was dissipating the heat. Is Dacron made of polyethylene terephthalate? Dacron is a brand name. That's the problem, is you usually have to work through the brand names. So why use liquid oxygen to react with kerosene as opposed to solid oxygen? Because getting oxygen liquid is hard enough. To cryogenically cool it more than that is it becomes not cost effective. It's just too difficult. And then you have to get the oxygen into a liquid or gaseous form for it to flow into the engine for combustion as well. So the solid oxygen would be a problem. So you really want to have fuels that are going to flow well, and the solid oxygen would be another problem on top of that. Okay, and what advancements in chemistry do you think would have to occur to allow commercial space travel to be possible? I think the lifting off from Earth, escaping Earth's gravity, is a big energy cost, and it's still quite dangerous. We had a space shuttle that blew up because there was problems with the rubbers that were used, the rubber O-rings that were used for the flowing of the liquid oxygen and the liquid hydrogen. The O-rings became brittle at liquid oxygen temperatures, so that was an issue. So I think we really gotta figure out a way to escape Earth's gravity in a more efficient manner. And people have talked about maglev. And sort of like a maglev launch system. So we might be using magnetic forces instead of using fuels, which would probably be more possible. Let's see, I don't want to miss any. Okay, good. Was there no environmental regulation during this time? I can't imagine how many emissions from all the kerosene combustion. Yes, there were environmental regulations, but they were not as strong. Remember, Silent Spring by Rachel Carson wasn't published until the mid-60s, and so this technology was being developed in a very loose environmental regulation environment for fossil fuels. Fossil fuels were considered, just everyday stuff. What improvements were made between the Apollo spacesuit and the spacesuit used for extravehicular activities? Now they can make them on standardized sizes. Although you can see in the last trip they had 2 female astronauts and only 1 spacesuit size to a female astronaut's body, which was very backward thinking. So the creation of spacesuits now is a little bit more standardized. So they don't have to be hand sewn. They can be created with more machining of the parts. But still, it is almost still a bespoke process. When these spacesuits were made, they were completely bespoke, and they were made to fit the particular astronauts that were scheduled to go on a mission. And so yes, stuffed animals can go into space if they have been cleaned ahead of time. All right, any other questions? Are there changes in temperature that ever require adjustments to be made to how the cooling suit works or is made so people can stay at an okay temperature? I think because there is such a very efficient thermal barrier made by the Mylar, that as long as you have the spacesuit intact, you really have to consider just what's happening with you and your heat output in the spacesuit space. So it's not so much about the outside environment, because the spacesuit is designed to really create that strong thermal barrier. So as long as you are not overheating in what you're doing, which is a concern. Let's say you have an EVA on the International Space Station, and you're trying to work a wrench to tighten up a nut or loosen a nut. I mean, you may be expending a lot of energy and creating a lot more heat, so that may be a problem. Any other questions? Can spacesuits survive a fire? Yes, to a certain extent. They're meant to survive a fire long enough for the person to evacuate the fire area. What would happen if a rat or something got onto the ship when it was taking off? The rat would be scared to pieces. If the rat was within the compartment with the astronauts, the rat would survive because they keep a pressurized atmosphere in there. But it would get bounced around a lot because it wasn't tied down into a launch chair. What aspect of the suit limits the time that can be spent in the suit on the EVAs? It's usually going to be the air handling. That's going to be the big part. That's the biggest limitation. I think the other limitations, such as heat, is going to be secondary, but really air handling is first, because you got to take everything with you. All right. Well, I really enjoyed this. I'm so glad I could give you an afternoon's perambulation through some interesting parts of our space mission history. Thank you so much.